Okay, hello everyone. So my name is Rocky. I'm a postdoc at Stanford. So I'm going to present my work on the exploration of different parameter optimization algorithms within the context of ACTS software framework. So before starting my presentation, I would like to thank Heather Gray. So my supervisor, Lauren, had a family medical emergency, which took her away for most of the year so far. And so in her absence, Heather stepped in and worked with us. So Laura and I are really thankful to you, Heather, for all the help. Okay, and so coming back to the presentation and the motivation for this work. So this flow chart here represents a broad workflow of broad workflow of the tracking algorithms. So we have tracking algorithms, and it takes in input as the detector and the simulated hits, and it gives in the output the reconstructed particle tracks, and that helps in calculating the tracking performance. But along with that, the tracking algorithm takes a number of input parameters. So these input parameters depends on a number of factors like the detector geometry and the material configuration and like pile-up, center of mass energy, and like many other factors. So depending upon these parameters, depending upon these factors, we need to tune these parameters to get a better performance for the tracking algorithms. And for the upcoming HLLHC environment, the high luminosity LHC environment, we expect more complex tracking. We'll have around 10 times more data every second, and there'll be around 200 pilot collisions. And so we need a more refined tuning of the input parameters in order to achieve a better performance. Okay, so and the current approach, the most popular approach right now is the hand tuning, where we by hand try to fix the different input parameters and see which configuration is working the best. So this can provide a good configuration, but this approach is very time consuming, and retuning is very hard if suppose something changes, there is a change in the underlying configuration or any other factor changes. So the retuning is very hard. So the new approaches are very much needed. So how about some automatic parameter tuning algorithms based on the tracking performance? So these kind of algorithms can be very efficient. They can be less time consuming and can help in easy retuning as well. So we have tried to explore this idea and study different optimization algorithms. These are the various derivative-free approaches. So we have explored 5 different approaches listed here. So the first approach that we have considered is the distributed evolutionary algorithms in Python, which we have referred to it as EA throughout the presentation. So this is an algorithm based on the genetic evolution in the living organisms. The second framework that we have considered is the Optuna hyperparameter tuning framework, referred to as Optuna in the talk. So this is an open source software used for the automatic hyperparameter search. Then the third algorithm that we have considered is the Lipschitz optimization, referred to as LiPo in the talk. So this is a very simple algorithm based on a mathematical model, and it doesn't have any hyperparameter of its own, which is very rare. And then the fourth one is the scikit-optimize, referred to as skopt in the talk. So this is an optimization framework built inside the Python sklearn library. And the last one is the Orion, which is again a black box kind of optimization framework, and have different optimization techniques. So the test bed for our studies is the Common Tracking Software Framework, ACTS. So as we have been already hearing a lot about it, and it is an open source tracking framework which consists of high-level track reconstruction modules, and it can be used with different detector geometries. It also has one inbuilt detector geometry. We call it generic or the TrackML detector, which is equivalent to a full silicon LHC kind of detector. This shows schematic of that detector. So we have used this detector to perform our study. So for the input data set, we have used a TT bar process with a pileup of 140 and 200 at 14 TeV. So we generated this data using Pythia 8 and simulated through this generic detector within ACTS. And we have used a minimum PT of 1 GV and absolute eta of less than 2.5 for our studies. Okay, and we have considered 2 different tracking algorithms for doing our study. So one is the track finder and fitter. So for that, we have used the combinatorial Kalman filter algorithm. And another one is the vertex finder and fitter. And so for that, we have used adaptive multi-vertex finder algorithm, AMVF. So in the CKF, the main bottleneck is the track seeding. So if we use the truth track seeds, we are able to achieve high efficiency. But if we are using the track seeding algorithm implemented in ACTS, we are having less efficiency and high duplicate rate and as well. So we have tried to optimize the track parameter, the input parameters of the track seeding algorithm while evaluating the performance on CKF. And for the AMVF, we have used the CKF tracks with truth seeds as input for the AMVF and optimized 5 parameters of the AMVF algorithms and evaluated the performance on AMVF itself. Okay, sorry. So the most important thing for these kind of optimization algorithms is how to evaluate the performance. And for that, we require a score function, or we also call it an objective function. So the objective function should be based on the performance metrics of the underlying tracking algorithm. So we have many quantities, and we want to give the positive weight to the quantities that we want to increase and the negative weights to the quantities that we want to decrease. So for the CKF algorithm, we have these 4 main performance metrics, which are the tracking efficiency, that is the fraction of the generated particle which are actually associated to reconstructed tracks, and then the duplicate rate, which is how many duplicates we have in the reconstructed tracks that are associated with the same truth particle. And then the fake rate is the fraction of reconstructed tracks which are not associated to any of the truth particle. And then the runtime of the CKF algorithm. And for the AMVF, the main performance metrics are the total number of reconstructed vertices. And then the reconstructed vertices tagged as clean, merged, split, or fake. So the clean vertices are the ones which are associated to one truth particle with more than 70% of the reconstructed tracks. And the merged are the one where we have 2 truth particles, but these are associated with one reconstructed vertex. And the split is the opposite, where we have one truth particle which is associated with 2 or more reconstructed vertices, and the fake are the ones where we do not have any associated truth particle to any of the reconstructed vertex. And then we have the vertex resolution, which is the difference in the vertex position between the truth and the reco in X, Y, and Z. So we have used these performance metrics for AMVF. So based on these metrics, we have tried to construct the score functions for CKF and AMVF. So for the CKF, we have this score function that we finalized after iterating over different versions. So we have given a positive weight to the efficiency and a negative weight to all the 3 factors. And we have given less weightage to the duplicate rate and the runtime by using this factor K, which is 7 for our algorithms. And we have not given any less weightage to fake rate because the fake rate is already very low for our algorithm. So this is not really going to affect much. So this is what we have for CKF. And for AMVF, we have 2 quantities that we want to increase. That is the total efficiency and the clean efficiency. And then there are the 4 quantities that we want to decrease. So we have given positive weight to 2 quantities and negative weight to 4 quantities. And we have specially given twice the weight to the clean vertices. So because we want to emphasize to have more cleaner vertices in our final result with the optimized parameters. Okay. And so how we have integrated the 2 algorithms. So this is our ACTS tracking framework, and this is our tuning algorithm. So we provide the list of the parameters that we want to tune and a minimum to max range to the tuning algorithm. And based on that range, the tuning algorithm suggests a set of parameters to the tracking framework. And based on those parameters, the tracking framework evaluates the performance, and it provides the performance to the tuning algorithm. The tuning algorithm evaluates the score function based on those parameters, and it tries to increase the score function. And in this process, it provides another set of parameters to the tracking framework. And so this keeps on going over many iterations, and at every iteration, they try to increase the score function. And one point that is to be noted here is that the tuning algorithm tries to keep a track of all the previous iterations, and this way it tries to improve based on all the history of all the previous iterations, and therefore after like hundreds or iterations, it provides a configuration which is giving us better efficiency and less fake rates or duplicate rate or whatever. Okay, so this is how we have integrated our algorithms, and so now I'm coming at the results. So for first we have the CKF optimization results. So we got the tune parameter from the different optimization algorithms, and we have the default parameter which were already there in ACTS, and we compared the performance metrics between the new parameters and the old parameters. So here is the tracking efficiency and the duplicate rate as a function of eta. So this plot shows the efficiency as a function of eta, and the black dots are the unoptimized parameters, and the other ones are the optimized parameters using different algorithms. So, so this is Optuna, EA, LiPo, Orion, and SKOpt. We have all the 5 algorithms, and we have optimized parameters. So we are getting higher efficiency even in the barrel region, and especially in the AND-CAP region, we are having very low efficiency for the unoptimized parameters, and our optimized parameters are able to achieve better efficiency in high eta region as well. And this is the duplicate rate as a function of eta. So we can see a quite nice decrease in the duplicate rate. So these are the duplicate rate before ambiguity resolution steps. So we are having very high duplicate rates, and so even before the ambiguity resolution step, these algorithms are able to reduce the duplicate rates. And so this slide shows the same distributions as a function of PT. So we have efficiency as a function of PT and duplicate rate as a function of PT, and we see the similar trend here as well. Okay, and this slide represents the table, shows the table with this, all the scores and all the different algorithms. So this is the default one. So we can see that we have a clear increment in the score for the different algorithms, and there is an increase in the efficiency. So all the algorithms are able to achieve almost similar efficiency, and likewise the similar is the case for the duplicate rate as well. And we can see that the fake rate is consistently small for all the cases, and we are also able to achieve less time for the tune parameter as compared to the default ones. Okay, now I'm coming to the Amv optimization results. So again, we compared the default and the optimized parameters for all the algorithms. And so this slide shows the reconstructed vertices, the total number of reconstructed vertices, the clean and fake. So I'm first coming at the clean and fake. So here the black dots represent the unoptimized total number of reconstructed vertices. So on the x-axis we have the pileup collisions, the true number of pileup collisions, and on the y-axis we have the reconstructed primary vertices.
Yes, we'll give you more time. But go fast.
Okay. So we are able to achieve get better, more cleaner vertices and less fake vertices using the using our optimization parameters. And for some of the algorithms are able to give more total vertices, and some are less. So this is basically a trade-off where it tries to give us more split vertices as well. So whenever we have more total vertices, there are more split vertices, and where we have less total vertices, we have less split vertices using the optimization algorithms. And the merged vertices are not showing much effect because these were already small. So we can see that in the slide that there is a nice increase in the cleaner vertices and nice decrease in the fake vertices using the optimized parameters over different pileup ranges. Okay. And so this shows the resolution in X, Y, and Z. So this is in X, Y, and Z, and we can see that in X and Y we have like more centralized distribution. So more vertex are closer to the truth as compared to the unoptimized one. We don't have much difference in case of Z. Okay, and then we did a study with our real detector geometry, that's Atlas ITK. So we performed some preliminary studies with using the Atlas ITK geometry. So so for that, what we did is that we used the Atlas ITK geometry, but we plugged in within the ACTS algorithm, because ACTS framework can be used to plug in different geometries. So we used ACTS Atlas ITK geometry and plugged in within ACTS and generated the TT bar data for a pileup of 200. And so we have studied the CKF parameters only for the ITK geometry for now. And we have used a minimum PT of 1 GV and eta of less than 4 for the study, and the score function are more or less similar, but we are using a k equal to 5 for all the algorithms for this case. And these slides represent the tracking efficiency and the duplicate rate as a function of eta for the ITK geometry within ACTS. So the black ones again are the unoptimized parameters, and the others are the optimized ones. And here is the duplicate rate. So we can see a good improvement in the performance with the tuned parameters or unoptimized ones. And this is again the plot with the as a function of PT. And so we see a good improvement here as well. Okay, so and as a conclusion, so we have studied different optimization frameworks, and we have achieved a significant improvement in the performance using the tuned parameters. And one thing that we have observed is that the optimization algorithms depends a lot on the score function, and we can tune them as per the need by providing different scoring functions and different weights to the different metrics. And so for the future work, we are planning to improve more on the integration of the optimization algorithm within ACTS, and will explore other approaches if possible, if needed. And then we are planning to have more detailed study with the Atlas ITK geometry, and also within Athena framework to use these tuned parameter within Athena, and if possible, that may be used in future for the actual data taking as well. Yeah, that's all. Thank you.
Thanks, Rocky, for presenting 28 slides in 60 minutes. In the old days, we would call this a Carlo Rubbia show. So questions?
Yeah. Yes.
I'm not sure if I understand correctly, but your duplicate rate is basically you reconstruct the same particle with two or more tracks, I mean, the same time.
Sorry, I don't understand.
What you call duplicate rate is instead of reconstructing one track out of one particle, you reconstruct several tracks out of one particle.
Yes.
Why is it so hard? And I mean, I see like 70–80%, if I understand correctly. I assume these are absolute numbers and not percent.
Well, the first reason is because we are working on very high pileup. So this is for a pileup of 200. So
that's a seeding. If you allow seeding in how the seeding setup is taken, okay, you can create several seeds per track, which are different because what is taken now is you like take 5 layers, so you can make different triplets combinations. So this is running without ambiguity solving yet.
No, but be careful. I mean, this is the ACTS prototype. This is not what Atlas usually shows as ITK tracking performance. And this is in the ACTS framework, and it is using the current ACTS tracking prototype tunings. And on that one, it's making good progress. So I mean, that's one has to put this in perspective.
Definitely, this is not like the unoptimized the black dots are not what the Atlas current results are. So they already have the tuned parameters. So these are the results corresponding to the default parameters that we already have in ACTS. So, but we are making improvement on top of that. So we are hoping that we'll be able to get like some improvements in with respect to the Atlas tuned parameter as well. Yes, Mark.
First, sorry,
keep on going.
To follow up, so if you change how in your score function, if you give this more weight, but does it decrease without compromising the efficiency?
No, it will compromise the efficiency.
Okay.
Yeah, and since I was already talking, I mean one of the you didn't show which parameters we were actually touching, but of course one of the things which at the end we want to have is that the reconstruction is robust against detector defects, which of course the model you are using in ACTS doesn't have so much of. Did you already think about strategies for doing that?
Not yet. We are basically exploring, and so I guess there's a large room for improvement in this work right now. So this is like we just started it like 6 months ago, and so we are here right now.
But
we really want to keep working on it.
It's a question to room actually.
And so we have the parameters that we used and all the details in the backup. So.
As usual, say your name before you speak. So we have 1, 2, 3, 4. Wow. 28 slides, 28 questions. Go ahead.
This is great. how many parameters are we talking about that you tune with this, and what are these default parameters? So how are they set?
So the default parameters are more or less, I guess, similar to the, I know some of them are similar to the Atlas ones, I guess. I checked them. So some of them are similar to the Atlas ones, and some of them, I don't know how they were giving those values. So these are the ones that are already there in the ACTS framework. And so for CKF, I have.
The ACTS one is a copy of the current ID.
She has the.
Yes. So I checked for.
It's not the one which is tuned for the ITK.
Yes.
I keep saying this because people might get confused, but.
Yes, of course. Yeah, so we already had a lot of fight because of that people don't get confused because of that. So yes, yeah.
Okay. Follow-up.
Yeah, so maybe it would be interesting to see also data points for, I don't know, students sitting one day, tweaking a bit parameters, how this compares to optimization.
I have those in the backup, so. Okay, so these are the CKF these are the CKF parameters that I have tuned. So so I mean there is the meaning of these parameters here. I have explained everything, so maybe anyone is interested. So, but I can just tell, like, this shows like the behavior of different algorithms. So here we have the default and all the other algorithms and all the parameters that we are getting. So basically, it's not that all the algorithms are giving you the same values. Most of the parameters are giving you different values. So I would like to emphasize on these two parameters. So here is the max PT scattering, and this last one is the sigma scattering. So these two are interrelated in the algorithm. And so suppose for EA is trying to give very small value to the max PT scattering, but it is at the same time it's trying to give very high value to the sigma scattering. And while the LiPo is giving very high value to the max PT scattering, but it's giving very small value to the sigma scattering. So it's basically trying to find local minima in so these two parameters are interrelated. So if you increase one, you decrease another, you will get high efficiency. So this is how they are just trading off between different parameters.
Yeah, this is exactly what I mean. If you have a human doing it, how does it outperform the human spending, I don't know, a couple of hours on
I think it's a number at some point. I mean, our code everywhere is full of tunable parameters. So that's actually my question to the room. If someone has a smart idea, ideally, that's kind of what we would like to arrive, is that you write your code and you declare, let's say, a parameter with a pragma or whatever clever way. You say tunable parameter of type whatever float in a range, and then you have it in the code like this, and then ideally you would have a service that collects all of those and then has an optimizer. And then this becomes practically a parameter optimization exercise. Yeah, but this is somewhat a vision we would have to put that as a service, that you can an auto tuning of, or at least the first tuning of your parameters in an automated way rather than like iteratively.
One challenge, Andy, is that I mean, I've worked in projects where we do parameter optimization, and the mathematicians tell us that, you know, with more than 10 parameters, it becomes fairly unstable. And the state of the art, I think, is something like 30 parameters. I mean, more than 30 parameters, you don't have an optimizer. Anyways, I think it was you next.
Yeah, it's Matthias. I actually don't know if I still have the question because we discussed already this slide. I actually looked at slide 39.
Yeah.
Where you have the values more than here, yeah. And they're so, maybe it's more a comment, because I mean, you optimize for totally different scenarios what that tracking can do at the moment.
Yeah.
So you see it with the zero, for example, or impact the max what you have there, for example. Yeah, I don't know. It's actually not a question. I need to think more about it. But basically, it's not.
Yeah, but that's
to
exactly what an automatic algorithm is doing.
Yeah.
If you leave it flowing, it discovers that there are large radius tracks, and it's going for the efficiency.
How many times have you?
Maybe just to comment on this point. So you can actually define quite flexibly, and I think Rocky showed this, right? What you actually want to optimize against. And certainly when we explored this, it depends strongly on what you choose to optimize against. So, I mean, for now, it's focused on efficiency, duplicate rate. The fakes actually didn't matter so much in most cases. But of course, one could think about adding in other types of tracks with certain weights to ensure that those weren't ignored by the optimization.
Heather, and I fully agree with you. I mean, the other thing, of course, is that this is TT bar with 200 pi lab, right? Yeah. If you do that and you have full true samples, you tune on min bias, where there's no physics at the end, right? So, and I mean, one of the things you might want to do is to optimize the scoring function when it comes to the efficiency, just to the signal interaction. Because then suddenly the network, whatever optimization algorithm you run, will discover that there's jet structure in the tops. You know? And that will give you you will automatically go to a different working point if you do that.
And one point also is that like we provide the minimum to maximum range also for each of the parameters, so that also matters a lot. Like if we need to really think hard on that, the range should be physical enough to.
How many times did you hit the minimum or the maximum? Did your algorithms hit the minimum or the maximum? Like how many times Optuna hit the minimum or maximum?
The minimum or maximum of the parameter
Yeah.
range? Very few times, like I guess.
0 for max hits, it looks like.
No, so that's I actually that's not 0. That's like it's in the algorithm. It's maxi SPM +1. So it's actually the default is 2, and all of these are saying that take 1.
Okay.
So it's like sorry for.
So incredibly, we are only 6 minutes late. So one last question, Jackson.
Yeah, this is Jackson. So I guess this is more of a general or broader question. So you showed here a lot of derivative-free approaches, and I guess I'm curious for the room as well, like how intractable would it be to like move towards making tracking differentiable, where you can then do gradient descent and all this kind of stuff.
We thought of that, and I even actually have a slide for that. Yeah. So yeah.
Probabilistic tracking.
So the main thing that I understood till now is that in case of the neural network, if we really want to do that, we can really write down the output in terms of the input. It is a like complicated differential equation where you have your output and all the input and weights and biases. But there is no such thing that we can do in case of the tracking algorithm. We don't have any equation where we can write the output in terms of the input. So I don't understand how can you make it like differentiable at the first place. So yeah, that's the main reason.
Right, you're essentially learning probabilities for the edges.
Right. So moving towards something that is intrinsically differentiable instead of something like it. Yeah.
If like someone has any idea about that, we would like love to hear that.
Yeah, there is, well, aside from doing neural networks, there is some crazy things called probabilistic programming, which you may have hit sometimes, but it's a little bit, cutting edge.
But, I think this Xiangyang, I think the one way is just do the surrogate models. The surrogate model itself is differentiable.
True. But the surrogate of the seeding of your score,
a relation between your score and your input parameters. Then you can impose some surrogate models. Of course, you will sample certain input variable to establish that surrogate models, and then you can make a prediction, say which parameter set will give you best score, and then you just iteratively can improve it. But normally, like for example, generated tuning, they just generate a certain set and then select a fraction of them, build a surrogate model, and do the parameter estimation.
Yeah, we'll definitely would like to follow up. Sure.
all right, we gotta move on. Thanks for talking again.